everyone. Okay, today we're going to go through the Test 3 review assignment that can be found on Mymathlab. We have Test 3 coming up. This is a great way to study for your upcoming tests. We'll just work through the problems. So for this first one, we have using polynomial long division. Okay, that if you look at the instructions, it talks about how to rewrite your answer. We'll talk about that when we actually finish the problem. So let's set this up. Okay, so we're dividing by x squared. Now notice that you have x squared plus 5. Remember that if you skip a value of x to a power, you have to put a 0 in that place. Otherwise, it will mess things up and you'll get stuck when you're trying to solve the problem. And then for the top, we're dividing by, you have x to the 4th. Okay, notice there's no x cubed, so we need to put 0 x cubed. Plus 9x squared plus 39. Okay. I'm sorry, that's a little messy. It's hard for me to write. Okay, so starting with this, it looks really big and long, but when you approach it, all you do is you look at the first term of the divisor and the larger function that we're dividing into. Basically, you just want to say, okay, I need x to the 4th. I have x squared. What do I need to multiply to give me x to the 4th? That would be x squared. All right, so from there, if you would feel better coming off to the side and just dividing the x to the 4th, the larger one, divided by the smaller, you could do it that way. And if you did that, you cross out, right, and you get x squared. It's the same thing. It just seems a little bit easier for me just to ask myself, what do I need to multiply to match up? My goal is to get x to the 4th. Once you do this, we multiply through every single term. Okay, so we have x squared times x squared is x to the 4th. Then we have 0 x cubed plus 5x squared. Okay, now it comes time to subtract. If we subtract, we are going to change the sign of every term and add. Okay, that's just a different way of looking at subtraction. You can define subtraction as plus a negative. So change every term and add. Okay, that gives us 0, 0, and then 9 plus negative 5 is 4. The x squared just comes down with it. Okay, so let's bring 8x. It's time to start over. So we have x squared here again going into 4x squared. What do I need to multiply to get 4x squared? Well, we have the x squared already, so we just need a plus 4. Okay, so we're going to multiply 4 by each term. So 4 times x squared is 4x squared, which is what we want because we want these to subtract out to give you 0. 4 times 0, 0x, and then 4 times 5 is 20. Okay, so in this case, notice we had the 20, so we could go ahead and bring the 39 down. That just happened where we brought both of those down. It just simply happened for this example. Doesn't always happen that way. But nevertheless, let's subtract and get our remainder. Remember, subtraction is, you can change every sign. The 0 doesn't really matter. And I'm going to change 20 to negative, and then you can add. That gives me 0, 8x, and then 39 plus negative 20 is 19. Okay, so we're done. This is the remainder. All right. So let's write our answer. Up here, this is called the quotient, and this is our remainder. So what they want us to do is they want us to write the answer as our quotient plus the remainder divided by or over what we divided by, which was this x squared plus 5. No need to write the 0 in it. Okay, so if you look at the directions, that's this part right here. Remember, this was the quotient plus, and this was the remainder divided by the divisor. Okay, so it looks weird in the directions, but they basically just want you to put your remainder over what you divided by. Okay, find the remaining zeros of f of x given that c is a 0. So they're telling us that 3 is a 0, right? So we basically need to say that we can divide 3. 3 goes evenly into the function, okay? So remember, if a 3 is a 0, that means that x minus 3 is a factor. Those just they go together, right? And this means that x minus 3, if I divided that into my function f of x, it would go evenly. That means there's no remainder left over. That's why we call 3 a 0. So what we need to do to work this is let's divide it. We're going to use synthetic division. Okay, let's do it right here. So we're just going to use the coefficients from our original function, which would be 1x cubed minus 4x squared plus 1x plus 6. Okay, and we're dividing by x minus 3, but in this case for synthetic division, we're going to use the actual 0, right, that was given to us. So let's work it out. Okay, so we bring the 1 down to start. Remember, we multiply, then add all the way down the table. We always multiply by the 3. Okay, so we have 1 times 3 is 3. We put it in the next column, and then we add these two numbers. Negative 4 plus 3 is negative 1. We start over. Negative 1 times 3 is negative 3, and add. Negative 3 plus 1 is negative 2. And finally, negative 2 times 3 is negative 6. We add those, we get 0. So remember, in synthetic division, this is the remainder. Okay? The fact that 3 is a 0 means that we should get a remainder of 0. Okay, so if you ended up getting something that didn't divide evenly, you've done something wrong. Okay, so what do we get? Our quotient. These numbers right here make up our quotient. So let's put the x's back in. We have 1x squared. Remember, we start with squared, which is 1 less than the original function. Remember, the original function was x cubed, so we start with x squared, and then we go down from there. So minus 1x, I'm just not putting the 1's in, minus 2. All right, so there's my quotient. There was no remainder. So to find the remaining zeros, you just factor this and set them equal to 0 and solve. Okay, you should be able to factor this if you get to this on a test. And this factors. Set each one equal to 0. You get x equals 2. Right, and this one, same thing, you get x equals negative 1. Okay, these are the remaining zeros, and that's what they want you to put because they asked for remaining. You probably know this from the homework by now. Look, the zeros of this problem, right, if you listed the zeros, you have 3, that was given to you, 2 and negative 1. Okay, so if I asked you for all the zeros, this is what you give. But in Pearson and on these problems, and this would be the same way on your test, they're asking for remaining zeros. So they only want you to list the 2 and the negative 1. Okay? Now, of course, if you listed the 3 in it, it would count it off. I would have to go back and check and give you credit for it. But if you can remember that, that would be great. All right, find the asymptotes. This one takes you through finding the vertical and the horizontal asymptote. So they really are completely separate. So let's first look at vertical asymptotes. Okay, so I'm going to rewrite this a little bit larger. Okay, so remember with vertical asymptotes, okay, so this is for the vertical, right? It's always in the form of x equals. All you do is you look at the denominator and it's where it equals 0. But you first have to simplify the function. It's very, very important. So see if the function factors. In the top, you can take out, let's see, a 3. And that gives you, what, 3x plus 2? But that didn't really help any because you don't have anything to cross out, okay? So you just want to make sure that's the case because you very well could have one where you do need to cross a common factor out. Okay, so your vertical asymptote is simply whatever makes the denominator 0. So you'll set that equal to 0 and solve. You get x equals 2. This is your vertical asymptote. So when you list it, it's very important. You must type in x equals 2, not just 2. because x equals 2 is the equation of a vertical line. Okay? Now, so that was A, x equals 2. Let's see, we'll put it right here. Okay, now for B, let's look at the horizontal asymptotes. Okay, now remember, with the horizontal asymptotes, this is one you ought to be able to answer in a few seconds. You basically look at the leading terms. Okay, the leading two terms are right there, and that tells you everything you need to know. So now in this case, if the exponents are the same, which they are, they're both 1, okay, then your horizontal asymptote are the coefficients right in front, 9 over 1, which is 9. Okay, once again, that's when you have the same exponents, x to the first over x to the first. Just take the numbers that are in front, 9 over 1, which is 9. So our answer would be y equals 9. That is my horizontal asymptote. Okay, make sure you put y equals. Very, very important. See, there's a difference because y equals is the equation of a horizontal line. Okay, if you come in and you write the vertical asymptote is 2 and the horizontal asymptote is 9, that is wrong. It has to be x equals 2 and y equals 9. Okay. Okay, here's another one with the asymptotes. I think we have 3 of these in the review. You probably won't have this many on the test, but it's good to work the different kinds. So let's first look at vertical asymptotes. Once again, remember for your vertical asymptote, you want to make sure your function is simplified first. So if it can be factored, try to factor it and see if there's any common factors to cross out. So let's do that first. At the top, we can take out a 3. That leaves us x plus 4. And on the bottom, it looks like we might have something. X and x, and what's that? 4 times 2? Negative 4 plus 2. All right. Okay, it factored. But once again, you can't cross out x plus 4 and x minus 4. You don't have common factors. Now, if that had both been x plus 4, you could cross those out, but you can't. So in this case, it is simplified, right? So now for your vertical asymptotes, it's going to be whatever makes the denominator 0. In this case, we have 2 things. So you just set each one equal to 0 and solve. X equals 4. Here's 1. And this one, x plus 2, you get negative 2. So in this case, we have 2 vertical asymptotes, x equals 4, x equals negative 2. Yeah, and you can tell up here where they want you to write the answer. 4 and x equals negative 2. I'm not sure if they might let you put a comma. Use a comma, I'll have to check on that for some reason. I'm not sure if they'll count off if you just said x equals 4 comma negative 2. I'm not sure. But if you want to be safe, you can write it this way. Write them separately. All right, now let's look at the horizontal asymptote. We'll do that over here. Horizontal asymptote. Once again, just look at the leading terms, and you can tell within a few seconds. Okay, so this is an example when you look at the leading terms, which is 3x over x squared. Look at the exponents. You basically have x to the first in the top and x squared in the bottom. So the exponent's larger in the denominator, and when that happens, your answer is y equals 0. That's always with the horizontal asymptote, when the exponent of the leading term is larger than the denominator. So my answer is y equals 0. Once again, don't forget, you have to put y equals and x equals. All right, and this is our third example about asymptotes, because I think this is one where there is a slant asymptote. So let's work through this one. First, let's look for vertical asymptotes. Okay, so vertical. All right, let's see if we can simplify. Can we factor this? Let's look and see. I'll try to see if this factors. I think it might. Minus and plus. That gives us negative 6 plus 1. So it actually factors. Once again, it doesn't do anything to help us. as far as for vertical asymptotes, you can't simplify it, so this basically is simplified. So my vertical asymptote is only what makes the denominator 0. X plus 1 equals 0, x equals negative 1. That's my answer. That is my vertical asymptote. There's only one. Okay, so now let's look at the horizontal. Does it say, determine if it has a horizontal or slant asymptote? So if we're looking for a horizontal asymptote, right, we'll look at the leading terms. And if you notice in this one, you have x squared over x1. Remember, for horizontal asymptotes, if it's larger in the top than it is the bottom, there is no horizontal asymptote. There is none. But there could be a slant. In this case, there is a slant. You have a slant asymptote when the exponent is 1 larger in the numerator than the denominator, 2 over 1. Or you could have, if it was x cubed over squared, it has to differ by 1. This case it does, so there does exist a slant asymptote. So to find the slant, you're going to divide the bottom, or the denominator, into the numerator. Let's see, what was it? Minus 5x minus 2. Okay? If you divided it, let's see, we have x goes into 3x squared. So we know we need a 3, and we know we need an x. We multiply the 3x through, right? 3x squared is 3x. All right, and let's subtract. So subtract, change both signs. We get 0, and we get negative 8x. Now we can bring down our negative 2, and one more time, x goes into negative 8x how many times? Negative 8. Okay? Actually, the quotient is your slant asymptote, so you really don't even have to finish the problem. The remainder has nothing to do with it. If you did finish the problem, you would multiply negative 8 through. Negative 8 times x, negative 8, and negative 8 times 1 is negative 8. If you subtract, you change both signs and add, and you would get 6 as the remainder. Okay, but for the slant asymptote, the remainder has nothing to do with it. It's only the quotient. Therefore, my slant asymptote is right here, and look, that's a line. Y equals mx plus b, right there. That's my slant asymptote. The function has a horizontal, let's see, the function has no horizontal asymptote. It has a slant asymptote of, and you would type it in right there, and that would be your answer. Remember, it's y equals, okay? That would be nice. I think they might count off if you put 3x minus 8. So just, it'd be great if you remember to put y equals. It's the equation of a line. Okay, now we get to the inequalities with our sign chart. So let's first look at a polynomial inequality. We always want to make sure that it's set less than or greater than 0. Well, it's already done for us. And the second step is we want to factor it. Well, it's already done for us here also, which is nice. So we want to find what we call our boundary points. You do that by factoring it, which is done. Set each factor equal to 0 and see what you get. If you set that equal to 0, let's see, you get x equals negative 3/7. Okay, so we have boundary points of 0 and negative 3/7. That's what we call, I'm pretty sure that's what they call this in Pearson, boundary points. Sometimes you'll see it or hear it called interval endpoints. They all serve the same purpose. This is what we're going to plot on our number line. We're going to make a number line. These are x values, so we're going to plot these. This is an x-axis. All right, it goes from negative infinity to positive infinity. All right, so let's plot them. So we have negative 3/7 and 0. Once again, these are our boundary points. So it divides the number line into 3 intervals. Now, I like to use straight and dotted lines. So remember, we're looking for where is this less than or equal to. If it's equal to, that means negative 3/7 and 0 could be part of the solution, because those are the two numbers that make the function equal to 0. So I draw a straight line. We have 3 intervals. This is where we pick a point inside each interval to test. Okay, by testing I mean, let's take, in this case, I chose -1. You could have chosen -2, -3, -4. Anything less than -3/7, and you're going to plug this in to our function. Okay, I'm going to write it up here. I'm going to plug it into my factored form right there. Okay, so when I plug -1 into x, I get -1. And when I plug -1 up here into -7, let's see, 7 times -1 plus 3, that gives me negative. Here, this gives you -7 plus 3 is -4. Right, so we basically have a negative times a negative. 2 negatives multiplied together gives me a positive. Okay, so I don't usually ever write the numbers that I'm plugging it in. You can just do this pretty easily. If you plug it into the factored form, all you care is it positive or negative. So let's try, oh goodness, something in between 0 and -3/7. It's kind of a little bit of a pain because you can't pick a nice whole number, but I'm going to pick something in between, something smaller, so I'll do -2/7. Okay, so if I plug -2/7 into my function, I get negative for the first one, right? And when I plug -2/7 into 7x plus 3, see 7, and I plug -2/7, that gives me -2 plus 3, which is positive. So I basically have a negative number times a positive. That ends up giving me a negative. All right. And then finally, pick something greater than 0. I'll pick +1. If I plug 1 in, I get 1, which is positive. Times 7 times 1 is 7 plus 3 is positive. 2 positives multiply together and give you a positive. Okay, so this is how you do your number line all the time. And if you move on to calculus, you'll have to do number lines like this too, where you just pick a point inside the interval, plug it into the function, and all we care is it positive or negative. Okay, so this tells us everything. Now we go back to write our answer. We're looking for, where is this function less than or equal to 0? Less than is a negative number, so this is going to be our, right here, this is our interval. Okay, so writing it in interval notation, we go from -3/7 to 0, and because we had straight lines, that means brackets. Once again, the brackets are there because we're looking for, where is it less than, right here, or equal to. Okay, and -3/7 and 0 are the two values that make it equal to 0. Everything else is less than. Okay, let's look at this polynomial inequality. To solve this, we first want to bring everything to the left side. So I'm going to subtract 49 over. Oh, sorry, that's a 49. And that leaves me less than or equal to 0, which is what we want. We always want 0 on one of the sides. So from here, we can factor it. This is a difference of 2 squares. So that's x plus 7, x minus 7. Right? And if you solve it for your boundary points, just set each one equal to 0 and solve, you get x equals -7 and +7. Okay, these are our boundary points. This is what we're going to plot on our number line. Okay, so let's do it right over here. Here's our number line. This is just like the last problem. Let's plot -7 and 7. I'm going to circle them just so I don't get mixed up with the other numbers. We need to draw our lines, straight or dotted. Once again, there's an equal sign in this. We're looking for less than or equal to. So these two values, a 7 and -7, are the two values of x that make this function equal to 0. So we're drawing straight lines. If it had just been as strictly less than, then I would have done dotted lines. Okay, we're going to test each region. I'm going to write this up here because I'm plugging it in. I like to plug it into the factored form so I can do my positives and negatives pretty easily. This is what we're plugging it into, x plus 7, x minus 7. Let's pick a point. So let's start anything less than -7. I'll pick negative 9. If I plug negative 9 in here, negative 9 plus 7 is negative 2. And then negative 9 minus 7 is still a negative 16. But that doesn't really matter. What matters is it's a negative number times a negative number. Remember, two negatives make something positive when you multiply or divide. So that's positive. The middle one, let's pick a 0 right in between. If we plug 0 in, we get 0 plus 7 is positive 7. And 0 minus 7, negative 7. So positive times a negative gives me negative. Right, and then we'll pick 8. 8 plus 7 is positive 15. Times 8 minus 7 is positive 1. So two positives being multiplied is positive. Okay, I know I did that pretty quickly, so if you have to stop and rewind it, but you just plug the number in, we get positives, negatives, and positives. Okay, so what are we looking for? We are looking for where is it less than 0 or equal to 0. So this is just like the last one. Happens to be the negative because it's less than. If I'd asked for greater than or equal to 0, you would have had two intervals, and those would have been the positive ones. But ours is the middle. So my answer goes from negative 7 to 7, right? So this is all the x values we're going to plug in, okay? And then negative 7 and 7 are our boundary points. So here we have it. Straight lines means brackets. So this is my answer. All right, now we get to the rational inequalities. These are worked just like the ones we just previously did, except you are dividing two small terms instead of multiplying. But it works the same. If you're dividing positives and negatives, that's the same as multiplying positives and negatives. And so for this one, we are going to find the boundary points by setting the numerator and the denominator equal to 0 and figuring that out. So the value for x that makes the top equal to 0, that would be, what, negative 1? You can kind of look at it and tell. And for the bottom, that would be 2. All right, I'm just assuming that you can set that equal to 0 and solve that pretty easily. So these are our boundary points. Okay, this is the part that is the only different part. When you are dealing with a denominator, you've got to remember that 2 can never, ever, ever be a part of the solution, okay? So the number that makes the denominator 0 is always a dotted line on your line chart, your sign chart. The reason is, if I were to take 2 and plug it into this function, I would get 2 plus 1 in the top, which is 3, over 2 minus 2 is 0, okay? 3 over 0, that is not a number. That is undefined, okay? Therefore, 2 cannot be a part of the solution ever. Even though I'm asking, where is it equal to 0? Less than or equal to, okay? Less than is going to work like normal. The equal to 0 is only the value that makes the numerator. Only the numerator. This is the most missed question during this whole test, okay? Is when people see the straighter than or equal to, or less than or equal to, they want to do straight lines for both, but you can't. So let's plot our boundary points. We have 2, and we have negative 1. Very, very, very careful. Since negative 1 is the one that made the numerator 0, that can be a straight line because negative 1 makes this equal 0. So let's think about it. If I were to plug negative 1 into here, into my function right here, I would get negative 1 plus 1 is 0, and negative 1 minus 2 is negative 3. Okay? Unlike the previous one, this one did not exist. This is the number 0. Okay? It all depends on if you have something 0 in the numerator or the denominator. All right, so 2, like I said, the denominator is always dotted. Please, please, please remember that, because this is what people miss right here, is they don't do a dotted line. Okay, so now let's test our values. I'm going to rewrite it. This is my function that I'm plugging into. So let's pick something less than negative 1. I'll pick negative 3. If I plug negative 3 into my function, I get negative 3 plus 1 is negative 2, which is negative. Divided by, let's see, negative 3 minus 2 is negative 5. Okay, a negative divided by a negative gives you positive. All right. Same thing between -1 and 2. We'll pick 0, which is nice and easy. So let's plug 0 in. 0 plus 1 is +1. And 0 minus 2 is -2. A positive divided by a negative is a negative. And lastly, let's pick 3, something larger than 2. So 3 plugged in, we get 3 plus 1 is 4, positive. And then 3 minus 2 is +1. Positive divided by positive is positive. Okay, once again, we're ready for our answer. Just like the last 3 questions, I really didn't plan well for this. I probably should have given you a greater than. So far, all 3 of our examples have been less than or equal to 0. So once again, this is the negative value. Okay, but I could have just as easily asked you greater than or equal to 0, and you would have had 2 intervals to list, right? The outer ones that are positive. So my answer here goes from -1 to 2. The lines are very, very important. Straight line means bracket. Dotted line means parenthesis. This is my final answer. Okay, let's evaluate the logs without the use of a calculator. The way we set this up is we set up a small equation. So I'm going to set it equal to x, and then we can solve it like an equation. We'll solve for x. Okay, from here with the log, we know that we just need to get rid of the log, and we do that by converting to exponential. So remember, we start with the base, right? So 7 to the x equals square root of 7. And now we can solve it using relating the bases. Right, we have 7 to the x, and I'm going to rewrite the square root of 7. That is 7 to the 1/2. So since 7 equals 7 and our bases are the same, then we can assume that x equals 1/2. And that's my answer. So log base 7 of square root of 7 is 1/2. All right. The next one, this one is use the product rule to expand the logarithm expression. Okay. From here we're expanding out. Let's see. We know the rule that says when we have a log and 2 things are being multiplied, like 9 times x, we can split them up and you add between the individual logs like this. Okay, from here, just expect to see a problem, but look for this, especially when asked, wherever possible, evaluate the log expressions. Hint, you might be able to do something further, and it all lies in this first part, log base 3 of 9. They want you to evaluate it, and we know from the log shortcut rules that we can write 9 as 3 squared. And when you have a log and the bases are the same, the shortcut rule says that all of this equals whatever that exponent is. So the log base 3 of 9 is the number 2. Okay, and then there's not much we can do with this. But this is what they want you to plug in for your answer. All right, use the properties of logs to expand the expression. All right, so let's see. We have natural log. Let's see, first we have a cubed. Okay, they're multiplying between them, so when we split them up into individual logs, we add between. And then for the bottom, the c to the 9th and the bottom, if you're dividing, that means you subtract the log. Okay, that's using the properties of logs, the first and second one. And then finally, if you have the log of a to a power, they want you to take these powers and bring them down in front. So that would be 3 natural log of a. Put that one down. That would be 3 of b minus 9 natural log of c. This is all they're asking. They simply just want you to expand things. Okay, so this next one is just going the opposite direction from the previous question. This time they give it to you expanded, and they want you to condense it into one single log. So your answer should be the natural log of something. So going backwards, we start. If you notice, you have the 5 in front of the natural log. We want to get rid of those. We want to put those back up as exponents right there, in the 4 and the 6. So let's rewrite it. That would be the natural log of x to the 5th. Natural log of y to the 4th minus natural log of z to the 6th. All right, So now that we have there, and it's all natural logs, now we're ready to combine into one single log. So remember what the rule is. We have the natural log, okay? When we add between the two natural logs, we multiply the terms. So those are multiplied, and the subtraction means we divide. This is what they're asking for. Make sure you include the natural log. I've seen people in the past forget to put the natural log and only do the x to the 5th, y to the 4th divided by z to the 6th. But if you don't have the natural log in front of it, you get the whole thing wrong. All right, let's combine these. Use the properties of logs to rewrite the expression as a single logarithm. Okay, we worked one like this in the homework. Remember, we have 3 terms, right? If you would like to rearrange these, you certainly could to make it, with the subtraction and the plus, that might be confusing on where to put things in the numerator or the denominator. The way I like to think about it is when you have a subtraction sign, that means you're going to divide out the term. If you have an addition sign, you're going to multiply, and it's going to be in the numerator. So let's see, that would be log of 4. We've got x squared. The first one. Okay, subtraction means we divide it, put the term in the denominator, there. And then this question here is right here, what do we do with this plus? We're still multiplying, but we're going to multiply, that means we're going to keep it in the numerator. Okay, like I mentioned this on the other video I did, and things didn't show up. If I wanted to put x plus 5 in the denominator, you would have had to have grouped right here. Group that together, and then you would have subtracted. You would have multiplied first and then divided the whole thing. But we don't have that, okay? So I'm going to undo that. Let's see, I'm going to erase. We don't have that. So I'd like to think of it, I know I keep saying this, but people mess up on this. If you see the plus signs, you put the term in the numerator. If you see the subtraction sign, put it in the denominator. And now we have this, and they want you to simplify it. Just expect if you see one like this, with something so big like this, you can factor it. And it should cross out. In the denominator, that's x plus 5, x minus 5. Okay, let's factor the x squared minus 7x plus 10. Okay, 10 is 5 times 2. Negative. Negative. Right, cross out what we can. We have x plus 5, x minus 5. So those crossed out, so our answer is nice and tidy. And there it is. Okay, now we're down to our last few problems. These are solving the equations, exponential, and then I think later on we have a few log equations. So for this one, for solving, we want to, if we can, relate the bases. And in this case, it looks like it. 49 we know is 7 squared. Right, so I'll rewrite that as 7 squared. And then we have, 1 over 7, all to the x minus 1. All right, so remember, we want to get 7 as our base. So we need to bring, look, this is 1 over 7 to the first. We want to bring that to the numerator. You can do that by, let's see, making that 7 to the negative 1. All right, and we've got our bases. Now, if you notice in this first part, remember when you have 7 squared all to the x, when you have let's see, an exponent raised to an exponent, you just multiply them. That's where I got 2x. And for the second part, you have to multiply negative 1 times each term. So we would have 7 to 2x, and that would be 7, negative 1 times x, and negative 1 times negative 1 is plus 1. Okay, so now we have 7 equals 7. Let's see, right here. So now we can say 2x equals negative x plus 1. Just set the exponents equal to each other and solve. Let's see, let's add x over. We get 3x equals 1. X equals 1/3. And that's my answer. Okay, let's look at this exponential equation. We have 16 to the x equals 64. This is one where we can relate the bases. We know that 16 is 4 squared, and 64 is 4 cubed. So we can write that 4 to the 2x equals 4 cubed. Since 4 and 4 are equal, we can set our exponents equal to each other and solve. We get x equals 3/2. Okay, let's look at this log equation. We've actually done one like this before. You have your log base 2 equals 2. Okay, in this case, to solve log equations, remember, we have to get rid of the log. Okay, in this case, the way we can get rid of the log is we can convert to exponential form. So let's do that. We can start with the base, which is 2. We raise it to the second power equals 5x minus 8. So just convert to log, convert from log to exponential. Then you can solve it. Do that quickly up here. That's 4. Go. Let's add 8 to the other side. 12 equals 5x, and it looks like our answer is 12/5. All right, here we are with the log equation where we have logs on both sides of the equal sign. So for this one, we talked about this before. When you have log equal to log, we've got to get rid of the logs. So you can just drop your logs in this case. So we have log base 5 equals log base 5. We can assume, okay, that x plus 1 equals 4x minus 5. Okay, so it's kind of like just dropping these. Okay, and then we solve from there. Let's see, I'll subtract x, get 3x, and add 5. I get x equals 2. X equals 2. You can always go back and check yourself if you want to. If you plugged 2 back in, you would get log base 5 of 3. And then if you plugged it into the other one, you would get 4 times 2 minus 5 is 3. All right, so that works. All right, so we're to our last two problems. These are exponential equations where we can't relate the bases. We look at 4 to the x and 25. Now 25 is 5 squared, right? But we can't get the same base, 4 and a 5. So what you can do is you can take the natural log of both sides. Natural log of 4 to the x equals natural log of 25. Okay? By doing this, and the reason we do this is now using the property of logs, we can take the x that's in the exponent and bring it down in front, and we get x times the natural log of 4. All right? And now we can just solve for x. Divide both sides by natural log of 4. These cross out. X equals natural log of 25 divided by natural log of 4. Notice it says in the directions, the solution is, simplify your answer. Use integers or fractions for any numbers in the expression, no decimals. So as you know in your homework, they ask you to take it a step further and plug it into the calculator. But on the test, you will not be asked to do that because we are not allowed graphing calculators or scientific calculators. So this is all you'll be asked to do. All right, and finally, we have another exponential equation. We want to take the natural log of both sides, but before we do it, let's divide out that 4 on both sides. So let's divide out 4, because we want to get e to the x by itself. So we have e to the x equals 31/4. All right, so from here, we can take the log of both sides. I'm going to do the natural log of both sides, right? Now we know from the properties, natural log of e, right, is just 1. So natural log of e to the x is just x. Okay, these cancel. So x equals the natural log of 31/4. That is your answer.